Anyway, feel free to write a research paper for your mother on your own this summer if you would like to. Yes, ma'am.
I gotta go to work.
Yeah, figure that out. So, okay, so we are leaving behind all of our electricity, magnetism, physics, all of that. We had a nice 6 modules, so we had a good 3 months covering physics after we did the chemistry and all of that stuff for physical science. And we're gonna move a little bit into earth science is to finish out. So we've got just the actual earth for this module. We've got the atmosphere that we're covering for the next one. And really looking at how do we tie in what we knew before to what we know now. That's the majority of what we learn, correct? Is how do we take what we know, apply it to what we don't know? How do they all work together for it? So as we move into earth science, let's see. It's called geology. Anyone's parent a geologist? They work for oil and gas. They might be a geologist, so you can hear that. Geology, the study of the earth, means just its physical, actual structure. Okay, so the composition, history, processes, all the things that act on it. So a geologist, you often hear of, that's a person who likes rocks. They might study rocks, how they were made, how old they are, how they break apart, what they're composed of, things like that. Okay. So as we look at our earth, and I have our nice little flow chart, because it's nice to have a chart to understand how everything really ties together for it. When we think about our earth, it's a big planet, right? So you go by and you see the pumping jacks that are drilled down. The furthest we have drilled into the earth is 8 miles. It's not very far at all when you think about how far it is across the earth. And so we get to see, in your book it talks about, we can see into space, we can see other galaxies, we can study stars and constellations, we can study other planets. And yet, we don't know that much about the planet that we actually live on by physical observations of it. So we can't see into the middle of the earth. We've only seen 8 miles down into it, which is not all that far down into it. So how do we get a picture of what's on the inside? You know, your whole life, especially in elementary school, they give you the picture of the earth. And they say we've got our crust, our mantle, and our core for it. Okay, how do they know we have these things? How do they come up with that picture of it? Well, a lot of it is from seismic waves. So we're going to draw on what we know before. We know that waves have to have a medium to move through, correct? So because unless they're an electromagnetic wave, which doesn't need a medium, a wave or sound has to have a medium to move through. So somewhere in the earth, we've got our tectonic plates and something moves and it causes some sort of vibration, right? So that vibration is going to spread out. We also know that waves don't just go in one single line, right? As we were studying with light, they spread out as well. So we've got waves emitting from a point that are spreading out like ripples, and it's going through different things. Well, if on Earth you've got a bunch of guys with seismographs in different places that are measuring seismic waves, so these are just a vibration that is emitted during an earthquake, you can take what each guy got and you can compare what did the wave look like at location number 1 compared to location number 3. And if it's the same wave coming from the same place at the exact same time, then what they look like should look exactly the same. So then what happens if it didn't look exactly the same? So that's what happened, is that scientists were able to back up and go, wait, we know that this wave was from this occurrence at this particular location at this particular time. Why did what Jonas got in Philadelphia look completely different than what Andrew got in Paris or in Taiwan? Okay, so we can deduce from what we know previously is that waves have to have a medium to travel through. That as they travel through things, what did we know about waves? They travel slower in air and faster in solids, correct? And so if it got there faster, hey, maybe it went through a harder part. If it slowed down, it had to go through something that wasn't as solid as the other thing that went through. So we get to start deducing and putting all these pieces in, going, something changed. And as a scientist, they are asking the question, what changed? We're always having those question marks, and then coming up with a plan. And it's not necessarily proof, but it's a thought until you can prove it otherwise, correct? Okay, so seismographs, has anyone ever been to the Science Museum and seen the seismograph that they have that runs nonstop? It has a little pin that hangs down on an arm that goes across. And as this is hanging, suspended, with only the effect of gravity on it, right? So if something underneath it moves, the suspended object is not moving. The object underneath is moving. And so it will move, and it will start, if you see seismograph papers, they'll look like little things like that. That's because we have a suspended pin, and then the paper is just moving underneath, and it's showing the movement of the earth because it's bolted in for it, okay? And so as they started analyzing all these different seismographs at different locations, they said, something is changing. As these sound waves that we know are being emitted from this one location, they're showing up at different speeds, different rates, different times, and different magnitudes for it. So the medium that they're traveling through is affecting where they're coming from, how they're getting to us. And so some of it is direct observation. Direct observation means eyes only. Indirect observation means we are deducing it from an event. Do you need our group class? Okay. Okay, so now that, and if you guys go on the Google Classroom, I've divided for this module, there's lots of fun extras. There's some biographies on seismographs and the scientists that did seismographs. There's some neat videos. So there's lots of extra resources at your disposal for this module if you want to on it. So when we look at the earth and we are making this information, we are deductive reasoning, we are going this, we've actually not seen this with our eyes, but because of the information that we've gathered, we're saying we believe this to be true. We can say that the earth, we can divide it in different ways. So we've got compositional layers, meaning composition, what it's actually made up of, right? In music, musical composition are the notes that make up that music. If you have a composition notebook for English, they're the papers that are made up of that. So compositional just means this is what it actually is made up with. So we are looking at the chemical makeup of it. Now mechanical, remember mechanical, the mechanics of something, how it moves, how it's actually put together. So mechanical layers are how the different layers, the physical properties, how they're actually put together. So that can help you remember the difference of it. So we've got those divided, and then of course we get to divide down further. So within compositional, they say we have a crust, a mantle, and a core. And I have a nice, I did bring a visual today. Sorry, I'm not prepared. Apple. My apple has a crust, a mantle, and a core. Okay, so right into it. If I were to compare my crust as the skin of my apple in comparison to the mantle, how much amount of the apple does the skin take up? Not very much at all, right? Then we would go all the way down through the apple parts, and we would eventually get to the core, which is right in the center, but is still not as much as the apple part, right? Well, watch that get brown and have a chemical event, right? What's happening? Oxidation. Good job. All right. So we've got our crust, our mantle, and our core. We've got a really thin layer around the outside, which is our crust. We have got a lot thicker layer. That is our mantle. And then we have our core on the very inside. Now, in that crust, we have two layers. So we're breaking that up. Once again, we have continental crust and we have oceanic crust. What does the continental crust have? What do you think that it contains?
Land.
Huh?
Land.
Land, continents. What is the oceanic crust? Oceans. You guys are so smart. Okay? So the difference between the continental crust is that it is thicker, so it actually takes up more space, but it's not as dense. Okay? The oceanic crust is thinner, but it's a lot more dense. What did we learn about density in water? What did we learn about density?
As you go lower down, closer to the core, it gets denser. Like everything gets compacted more.
It is compacted more. Someone, Jonas, what did you say?
It sinks more.
Denser objects sink, right? So if it's less dense. So part of the continental crust being less dense than the oceanic crust, do you think that's part of God's plan, that the continents stay above the water or stay up because they're not as dense? Those parts of it? Yeah, so we're still, in every area, we're able to tie back old information that we have and go, oh, this is a density thing. That makes sense that that's the land. It's on top, even if there's groundwater or things underneath it. So we also have, like you said, with the pressure, as it gets lower, it's going to compact it more, so we have something that's a lot more dense. Okay. Then, when we have our mantle, it contains these three areas called the lithosphere, the asthenosphere, and the mesosphere. Okay, so there's different layers of that. And then core, we have an inner and outer core. So when we talk about our mechanical spots, so the properties here, we can see that the mechanical properties are also a subcategory underneath our compositional properties. So we're just dividing them up. And I like mnemonics to help us remember. So from the outside in, we have llamas are moving over ice. Okay, so we have lithosphere, asthenosphere, mesosphere, outer core, and then our inner core. And this is going to go from the outside surface of what you see down to the inside when you need to know the order that they're in. Okay. Let's see, what else do we have? Okay, we already talked about that. Let's see. So when we are looking at the crust and what we have and of our core, we get into rocks and different information, okay? So there was a guy, his name was Mohorovic, and so they shortened it to Moho. We like that, okay? You're gonna see this word a lot. You will see the word discontinuity a lot. In it, you will also see, when we get to the atmosphere breaks, they call it, wait, what? I can, over there, maybe not. We're going to have, we've got these little breaks, and all it means whenever they talk about a discontinuity is discontinuous. In math, if a graph is discontinuous, it means it doesn't go from one section to the next. There's a break in it. So it doesn't mean that our earth is broken at that spot. It just means whatever we were talking about here, we're talking about something different over on the other side as soon as we hit that break. So it's like the doorway. So that's what a discontinuity is, okay? So most of our crust, the earth, is made out of silicates, silicon dioxide. Could you write that formula? If they said in your book, they just say silicon dioxide. They don't tell you what the formula is. I wrote SiO2. Would that be correct? Silicon is Si. Silicon dioxide. Yep, if you look it up. So as you start reading and you're seeing things, tie in your old information and go, oh, I know about that. Okay? So typically in your crust, we've got these different silicates. Here it says they're rich in iron and magnesium, and they're denser. Then we go to the mantle. And so on this inside part, so here we have a harder section of our apple, and then we have the inside of our apple. Is the inside of our apple liquid? Okay, is it the same density as water? No. But is it softer than the outside? Yes. Is it softer than the core? Yes, it's softer than the core. The same is with our earth. So we have our mantle here on the inside, and it's called plastic rock. That's what they call it. And we're gonna make oobleck. A lot of people, that's our word that we use a lot, like in our fun science things, and you've gotten to use it before. So we'll make oobleck today, which is like that. So it's not liquid, but it's not solid, but sometimes it behaves as a solid and sometimes it behaves as a liquid. It gets to do both things. So that's the difference there. So with pressure, it gets harder, and as pressure releases out, it gets a lot more liquid for it. Okay? Then once we get all the way down to the core, first we go through one more boundary called the Gutenberg discontinuity. So again, it's discontinuous, not in the fact that it's separate, but that there's a break, and what we were talking about, now we're talking about something different. So it's another boundary change, and it says it is mostly liquid iron. So if it is liquid iron, why is it solid?
Because of the pressure.
Yes, because of pressure. So you'll start reading, they give you a term called pressure freezing, okay? So with pressure freezing, you are pushing things so close together that if I have these atoms, I'm locking them in so tight that now they are becoming a solid, even though it was initially liquid. Now, so then that leads us to a question. Can you pressure freeze water? Okay, you're shaking your head no. Why?
Ice is less dense than water.
Ice is less dense, okay? So because water has the property that says for it to be a solid, so everything else, for it to be a solid, it has to get closer, right? But for water, our rule was for water to be a solid, it has to spread out and it has to lock into a certain grid. And if it's in the grid pattern, then it's a solid. But if it's not in its locked grid pattern, and it's just random even if it's closed, then it's a liquid. So pressure on water makes it go to a liquid state. So we can never have pressure freezing with water. Okay? So then with rocks, as we know that we've got, let's look at this one. It says core and magnetic field. So we already know that when we have mass, we have gravity. We know that as we align up our different poles, then we get more magnetism, right? So the magnetosphere is Earth's magnetic field, okay? And that means Earth is radiating some sort of charge, right? It has a charge. And that charge, the positive parts of the charge would be deflecting any positive that's coming in from the atmosphere, right? And the negative part of the charge would be deflecting any harmful negatives back out. And God created that so that as the sun, is sending out all of its rays, that the earth itself is deflecting out any of the harmful charges that are coming in, okay? So in our rock lithosphere, so this is our very top part, it's the very outside part there, we've got lots of dirt. And so we've got a couple of different things. We've got dirt, Soil, sediment, and rock. So it says soil is just the top layer. Sediments are fragments of rock like gravel, so things that you could settle out. If we were to pour a bunch of stuff in water and it would settle at the bottom, that would be your sediment that would have settled out. And then rocks, actual hard rocks, it says made up of different minerals, crystals, shells, and plants. So we've got 3 different types of rocks. We have sedimentary, igneous, and metamorphic. Okay. And to me, there's really only 2 different, because metamorphic comes from sedimentary or igneous. Right? So you can't have the third without having the first 2. So we have our sedimentary, our igneous, and our metamorphic. All right? Sediment means that stuff that is settling out, when we pressure it together and we add some chemicals, then it might start combining into rocks. And I have one here to show. And you can pass those one around, and you can see the different layers. Right? So you guys can pass that one around. That is a sedimentary rock. As each part comes and settles, we have different layers of material that are settling together, and then they're getting cemented. So it's almost like taking a couple of pieces of cardboard, gluing them together to getting something thicker. Or if you're a woodworker and you need to get a thicker piece, you might glue several boards up to get it the thickness. You can just leave it there. Thickness that you want. So that's how we get our sedimentary. Igneous is specifically from molten rock. So igneous we're looking at from lava is when it makes it to the surface. We're looking at molten rock, so this is melted. So if we're looking at igneous, we're looking at high temperatures, right? So we're looking at something that's really hot there. And then metamorphic comes from these 2 changing form into that one. So when we take sedimentary and we change its form, it becomes metamorphosis. Have you heard of that with caterpillars? And a metamorphosis, so from one thing to a completely new thing. So if it starts as sedimentary and now it's something different, it's metamorphic. If it started igneous, now it's something different, it's metamorphic. And the things that we know can change stuff. Pressure can either break it apart, it can break the bonds of the molecules, right? Pressure can also cause pressure freezing, and it can even freeze things together. So it can either break it apart into a different form, or it can cement it together into different things, or heat. You know that heat changes that a lot, okay? We talked a lot about minerals at the very beginning of the year whenever we were setting all of our chemicals. So we have these natural occurring minerals, or we have, it says there's not man-made ones, inorganic ones, and then different crystal structures. So as our minerals and our atoms are coming together into our compounds form certain minerals, we can describe them because they have a specific form. We can look at it and say, oh, this crystal structure looks like this. And then we always know that carbon always looks like that. Or sulfur always looks like this. Anyone been to the Salt Plains up north of Enid, whatever, okay? I wish I had brought some of our rocks. It is the only place in the world where the crystals form an hourglass shape. Okay? Do you remember what they were called? Hourglass gypsum. There we go. It's the only place that they form that. But every single one that you find will have an hourglass in it. The way that the crystal structure has set up, you can see the hourglass in it. No matter, there's little bitty ones, and there was really big ones, but they all had an hourglass in them. And that defined that type of mineral. So when we're able to kind of say that, just like if you were to look at your family, if someone were to look at your family photo and say, oh, I now have this group of people and I might have 5 family photos. I could say, oh, that person belongs in this family. Because you have characteristics of a sibling, you look like a sibling, you look like a parent, because you share the same DNA. So it makes sense that you look like them or resemble in that. So that's the same as we look through our crystal structures. We can look at a crystal structure and say, oh, we know that this belongs here. It has the same part of it. And the different ways that we identify our rocks are these 6 areas. And in your book, on page 363, if you haven't done that in your notebook already, it's going to be part of your assignment for today. It says, it gives you a list of different rocks, and you're welcome to turn there if you want to look at it. So we've got sedimentary, igneous, and metamorphic first, and then over on page 365, it gives color, streak, luster, hardness, fracture, and cleavage. Okay. And 364. And so what I have done is I have brought a set of rocks over here. And what I would like you to do is find at least 2 examples of rocks to fill in the different areas. And these are ways that we can define or classify the rocks that make up our crust and the lithosphere of our Earth, okay? So crystal structure just tells us the shape that it's in, just like our hourglass gypsum. With color, sometimes you can look at a rock and it will always be a certain color because that's part of its property. And so there's some rocks in there that have different colors for it. Streak is interesting because when you take your rock or mineral and you pull it across a porcelain hard surface, it will leave a color. They will often leave a color. And sometimes the color is not the color of the rock. And so often, like there are some black rocks, like hematite is a black rock that actually leaves a green, like a greenish yellow streak. And so you're like, oh, that has a completely different color than what I would have thought just by looking at it. So just because that's the color that you see, remember, why are we seeing a certain color? What do we learn from the light? So I'm looking at a black rock. Why does it look black to me? It's reflecting no light. Okay, but the light colors were different than the pigment colors, correct? So it can look black because it's reflecting no light, yet have pigment colors that are different colors. And so we find those pigment colors whenever we use the streak. And then that portion of it, because it's been broken apart, might reflect different light, and so we see different colors in that. Okay? Luster is simply how a surface reflects light, how shiny it is. Luster is used in woodworking. If you like, what's the luster of a table, or if you're waxing a car, or if you're getting photos. Anyone ever ordered photos and they ask if you want glossy or matte? Okay. Sometimes the drop-down box will say luster on it, and then your categories will be glossy or matte. Glossy means it's going to have a shiny surface. Matte means it's not going to have a shiny surface. You're not going to have the reflection of the light. And there we get there. Hardness is based upon the Mohs scale. M-O-H-S. Mohs scale of hardness. And it goes 1 to 10. 1 is your soft. 10 is the hardest. Who knows what the hardest is? Diamond. What is something that you are currently using that would fall in the soft range? Graphite. Found in your pencil. Okay? Graphite is soft. It is found in your pencil because it is soft, but because of number 6, fracture and cleavage. Okay? Fracture and cleavage is how does this mineral break apart? Is it super hard to break it apart? or does it come across apart differently? So graphite, if you were to look at it underneath a microscope, look at its structure. It is in bonds that are sheeted together. Okay? So the different parts are broken. So we've got really tight bonds that are bonded in one sheet or one line, but we've got these really weak bonds that keep the sheets together. So we are able to pull off a sheet or peel off a piece of it, one piece at a time. There are, what are those? I'm trying to think of that candy bar that I like. Oh, Kit Kats. If you eat the chocolate out on the outside of the Kit Kat, you know you have the different layers of the wafers. Like you can peel the different parts. You can peel it off one at a time, the different layers of it. So if a mineral has it where it can come off in sheets like that, which is an example, that's called cleavage. So you are breaking it upon a very well-defined plane. You know exactly how to break it. You can just get your chisel in there and pull it straight off. Fracture is it's going to break in a spot that is weak. So if you have a rock and it's got a bunch of parts and it is a sedimentary rock, which means if it's sedimentary, that means it's made up of several different types of materials, correct? Because they've all been glued together. It's going to be easier to break off a type of material than it is to break the different pieces of material out of it, correct? So when we have fracture, we are splitting it and we're breaking it according to the types of the material where those bonds were weaker between it. Does that make any questions about the difference between fracture and cleavage? Okay. All right. The rock cycle, you have this picture in your book, and it says it's the series of processes that cause rocks to constantly change. Because if I have a rock and I break it now into a bunch of pieces, and we have some sandstone here from our house that I think is pretty neat. So sandstone is a rather soft rock. It would be on the lower end of the Mohs scale. Okay. It is a sedimentary rock, meaning that it's a bunch of different pieces of other types of rock that are all cemented together. So it's a bunch of little pieces that we've gone together. And my guys have been able to shape these rocks into different shapes. So one made a cube, one made a nice triangle, another made an Easter egg. Okay? Same chunks of rock, they were able to shape them. They were able to sand these down because of fracture and cleavage, because they were able to break parts off of it. We've got this hardness of it. And what happened is, as they're sanding, what's happening at their feet? What's showing up on the ground? Dust, a whole bunch of dust. So they've got this sedimentary rock. They are causing weathering and erosion from it, correct? They're eroding part of it away and turning it into more little bitty sediment. Okay, so now we could take all of that dust and gather it up, and with heat and pressure, we could turn it into something else, right? It could be turned back into another one, or I can go dump it in the pond and it will settle out to the bottom. It will mix with mud, and now it will become a new substance as well, okay? Or this sedimentary rock, I could take a hammer to it or put a lot of heat and pressure on it and turn it into a metamorphic rock, right? We could take an igneous rock, so a piece of pumice, and break it with a hammer, causing weathering and erosion, and it would also turn into sediment. So what do we notice? We have igneous, metamorphic, and sedimentary that all break into sediment, correct? Now, when sediment is compacted, does it go into igneous? No, so compacting sediment turns it back into a sedimentary rock. Okay, so we've got three ways to get a whole bunch of dust. We've got one way to make that dust back into rock, or when we can melt a rock and turn it into magma. We can then cool it quickly and get a couple of different types of rock. So lava is rock that's made it to the surface. We have, whenever it cools slow, it makes large crystals. For the igneous rock, when it cools really, really fast, it makes really tiny crystals for it, so that changes it. Or we can go through heat and pressure straight across. So this is a good example of how what we have is not always staying there forever, just like we did with energy. Energy is always moving, but it's neither created nor destroyed. So if we want one thing, it has to come from somewhere else, right? So even with our matter, it's not created or destroyed, it's just changing forms through that. So we're gonna go have some fun, make some oobleck, and get to play around with that. Then make sure and open your notebooks to page 363. And what I would like